Here we are, last day of class. Beautiful sunny day. I'm feeling pretty good. Feeling better today than I did on Monday and Wednesday. So I hope you're feeling good too. Today we will do another Galois theory example, and instead of having the polished results up on the slides, I'm going to try to go through the process of trying to illustrate how to figure out what the Galois group is. I'll briefly talk about some advanced topics that are often encountered in graduate school, just in case there's a few of you who might be going on to graduate school. And even if you're not, I hope it's of a little bit of interest to you. And then we'll review for the final exam. I'll go over the things that I sent you yesterday in that message, the types of problems are on the exam. And I did decide I do want to put a couple short proofs on the test to add to those problems. I do want them to be short proofs. Nothing, no real one-page proofs, like half a page at most, maybe even less. All right. So what's the example I want to consider? Well, before we do that, we should probably review the fundamentals, definitions. Again, if you've got a field, just like with groups, you can consider the group of automorphisms of that field, which would be isomorphisms from the field to itself. Auto, again, means self. Isomorphism meaning, well, with ring isomorphisms, doubly operation preserving both addition and multiplication, and also one-to-one and onto. And it does still form a group. What's the operation? Function composition, you got it. All right. Maybe that would be a question in the exam. Describe what this group is. Okay, and say what the elements are and what the group operation is. Let E be an extension field of F. So now we're in our typical situation with field theory of imagining a base field and an extension field that's bigger. You know, it's kind of strange. Contrast this with group theory. We always think about, here's a group. How do we understand the group? We understand it by looking at its subgroups. With fields, we count a field. How do we understand the field? We look at an extension field. Well, maybe that doesn't help us understand the original field so much, but it at least helps us do our main task, which is to adjoin zeros of polynomials. To, for example, with Galois' goal to ultimately prove that a quintic is not solvable by radicals. It's a different kind of focus. It's interesting that way. Anyway, so you got an extension field, E of F, Gal E slash F, meaning the Galois group of E over F, is the group of all automorphisms of E that do one more thing. What else do they do? Don't look. What else do those automorphisms of E do when they're in here?
Map all elements of F to itself.
Yeah, they map all elements of the base field F to itself. They fix F. They keep F fixed. They map everything in F to itself. Not necessarily everything in E that's not in F. So something here could get mapped to something over there, but everything in here gets mapped to itself under elements of the Galois group. The Galois group is going to be a subgroup of this thing. Could equal it. They could be the same, but it could be also a proper subgroup. And I mean, it's kind of a head scratcher. Why consider such a thing? And the reason is because of the Fundamental Theorem of Galois theory, which again I'm not going to state because you should have seen it in the book. It's a real long statement. Kind of hard to understand. If I was going to state it and talk about it, it would take 25 minutes probably at least. Talking about it more verbally, I'm not going to have you state it on the exam, but you should know basically what it says. You get this natural correspondence between the lattices, the lattice of subgroups of the Galois group and the lattice of fields of the field extension. What are the subfields of E that are also field extensions of F? There's that natural correspondence both in the structure of the lattices, how many nodes and how many vertices and edges you could say, and also with the numbers that we put on the edges, which correspond to indices for groups and degrees for fields. Talk about it in the context of our example as well. Here's an alternative notation you'll sometimes see. It's It's not in the book, but just for your information. And it's helpful then to make this correspondence as well by going the other way. When you've got a subgroup of the Galois group, you can define a corresponding field called the fixed field of H, denoted by E sub H. Set of everything in the field extension E that gets mapped to itself for all elements of H, this subgroup of the Galois group. So once again, the fixed field of the entire Galois group, E sub that, it's going to turn out it will be F. Certainly everything in the Galois group fixes everything in F. And it turns out, at least when the characteristic of F is 0, and when we're talking about a field extension E that can be thought of as a splitting field for a polynomial, at least under those conditions, these are going to be equal. Okay, that's going to be not just that this is a subset of that, but these are going to be equal to each other. Okay? Don't worry about those extra conditions that I just mentioned. Every example we consider, this is going to be true. On the opposite end, if you consider the fixed field of just the identity mapping, epsilon, the identity on E, it's going to map everything in E to itself. That's going to be then all of equal. And then you've got the stuff in between. What are the subgroups in between, and what are the subfields of E in between? So here's our example for today. Phrased a little differently than the examples we considered on Wednesday. Phrased this way: find the Galois group of the polynomial f of x equals x to the fourth plus 1 over the rationals q. Find the Galois group of the polynomial f of x equals x to the fourth plus 1 over q. I didn't phrase it that way before. I just said, here's an extension field, E of f, find the Galois group of E over f. This is phrased differently. Find the Galois group of a polynomial. That's different. But we can relate it to fields. The Galois group of the polynomial over Q is going to be the Galois group of its splitting field over Q. Galois group of a polynomial f of x in capital F of x over the base field capital F is the Galois group of the splitting field of little f of x over capital F. So before we can figure out what the Galois group is, we need to figure out what is the splitting field. X to the fourth plus 1. Its zeros are going to be fourth roots of -1, right? X to the fourth plus 1 equaling 0 is equivalent to x to the fourth equaling -1. So once again, we want to use this information, this knowledge that I've been telling you about with how to multiply things in the complex plane, which you really should know about as a math major, even in topics of math, they do something different next year. There's the complex plane, the real axis and the imaginary axis. Here again is the unit circle. One I, -1, and -I. Radius of that circle is 1, it's centered at the origin, which is 0, which is the additive identity in complex numbers. -1 is right here, of course. It's a distance of 1 unit from the origin, and the angle that it makes with the positive real axis, its polar coordinate, is 180 degrees, pi radians. So, I'm looking for numbers whose fourth power is -1. Since the distance to the origin would have to keep getting multiplied by itself, these fourth roots of -1 must be 1 unit from the origin as well. They must be on this unit circle. And since the angle adds, I'm looking really for, at least initially, maybe the smallest angle such that when I add to itself 4 times, when I multiply it by 4, I get 180 degrees, 45 degrees. There's a 45-degree angle. This number, which I'm going to call omega, is cosine of 45 degrees plus I sine of 45 degrees. Of course, if I was using radians, which you should feel comfortable with, 45 degrees would be pi over 4 radians. And that's 1 over root 2 plus I over root 2. That's what that is. Representing here, realizing I can think about polar coordinates and then figuring out what the real and imaginary part are based on. So that's going to be a fourth root of -1. But there are 3 more that are all in the unit circle, and are 3 other points whose angles, when multiplied by 4, give you an angle that matches. Not necessarily 180 degrees, but maybe, for example, 360 plus 180. 540. 540 divided by 4, what's that? 135. 135 degrees. Yeah. There's another one at 135 degrees. Zoom in if that's too small there to see. 135 degrees. I could also think about negative angles if I want, or I could think about bigger positive angles. The other 2 are going to be here and here. You can think of this as negative 45 degrees if you like. Or positive, what would it be, 315? Yeah. And this one is negative 135 degrees. Should also know what the notation for complex conjugate is, if you've never seen it. When you take the complex conjugate of omega, that means you change this plus sign to a minus sign. That's going to be this point down here. This is standard math notation, so everybody should know it. If you don't know it, you're looking at it right now. Put a bar over it. That's its complex conjugate. It also, if you think about it, does happen to equal omega to the 7th power. Right? Because omega to the 4th brings you over here, then omega to the 5th, 6th, 7th. The subgroup generated by omega under multiplication is cyclic, of order 8. Omega to the 8th brings you back to 1. It's an 8th root of positive 1. And it's a 4th root of negative 1. This point down here is the opposite of omega to the origin, but it's also omega to the 5th power. It's both the additive inverse of omega and it's also omega to the 5th power. And this point would be omega cubed. There. I would be omega squared. -1 would be omega to the 4th. Negative I would be omega to the 6th. And 1 would be omega to the 8th. Also omega to the 0, omega to the negative 8, etc. Omega does generate a cyclic group of order 8 under multiplication. We talked about that a while ago, right? I made a Mathematica for that. Maybe around lecture 15 or something, I don't remember for sure. Okay, so anyway, so the splitting field, what are the roots of this? The roots of this are going to be the black dots, omega, omega cubed, omega to the 5th, and omega to the 7th. E, the splitting field, I could write this way. The smallest subfield of the complex numbers containing both the rationals and these four elements. That could be in the test. Define what this kind of symbolism means. This is a subfield of the complex numbers. It's the smallest subfield of C containing all the rationals and containing these four complex numbers. It's going to contain plenty of other things too. For example, it's going to contain omega plus omega to the 7th, for example, which is not rational. It's also not one of these things. In fact, if you think about it with the picture, if you think about it, these things as vectors, and think about the parallelogram law, if you add omega and omega to the 7th, you're going to get a real number. They're complex conjugates of each other, omega and omega to the 7th. You're going to get twice the real part. You're going to get square root of 2. Square root of 2 is in this field, and you probably wouldn't have guessed it beforehand. Because it's not like we're adjoining the square root of 2, so it's a little misleading that way if you think too simplistically. But this is a field, so it's closed under addition. Omega and omega 7th are in it, and therefore their sum is in it, and the sum happens in square root of 2. Another example would be adding omega and omega to the 3rd. Adding these two things, think vectorially there, it's going to bring you to a purely imaginary number up there. Not drawing that well. And that number is going to be twice the imaginary part of this times I. It's going to be square root of 2 times I. And that's in this field too. But can we simplify this? Can we write it so it's not like we're adjoining 4 elements. Can we write it as a simple extension, Q of A for some A? And there was a theorem that said in this kind of situation you can. And it's good enough just to do omega. If you put just an omega there, again, this is a field containing omega. It's going to contain all its powers. It's going to contain omega cubed, omega to the 5th, omega to the 7th. It's also going to contain omega squared, omega to the 4th, omega to the 6th, and omega to the 8th. It contains I, negative 1, negative I to 1. I mean, you already knew it contained 1 and negative 1. Omega to the omega squared is I, and omega to the 6th is negative I. Those are in this field too. So again, so little warning not to think too simplistically. It's not like you're taking Q and just adding 4 elements. You're adding infinitely many more elements than you had to start with. I mean, you had infinitely many elements to start with. You are unioning it with a collection that's also infinite, even though you only see a finite number of things in it. You should be able to describe what this means, though. Not just in this case, but also in general. Describe what this notation means. And by definition, it's a field. It's not something you have to prove. Smallest subfield in E containing F and all these elements. Anyway, that's the splitting field. We're after the Galois group of that splitting field. We want to determine its order. We want to determine its isomorphism class. We want to describe its elements. We want to determine the fixed fields of its subgroups and draw the lattice diagrams. That's the question now, is what is the Galois group of Q of omega, Q adjoin omega, over Q. And this is the hard part now, right? What do you do now? Well, any automorphism, well, first of all, I mentioned in the last lecture that in the context of field extensions of Q, any automorphism of the field extension that contains Q is automatically going to fix elements in Q. So what I'm trying to say is, in this situation, the Galois group really is the same as the group of automorphisms of that. Not necessarily in general, but problem 1 in chapter 32 said that when you got field extensions of Q, like we do have here, any automorphism of the extension field is automatically going to fix elements of Q. And so these two things are going to be the same. Not necessarily true in general. Certainly, as always, the identity is in there. So at least got one element. It's the identity on the extension. Its formula is epsilon of x equals x for all x in the extension field. Okay? But that's the easy part. What's the hard part now? To help you figure out the other elements, it's good to realize let me call this E just to save a little time. It's good to realize that any element of the Galois group is going to permute the roots of the given polynomial. F of x equals x to the fourth plus 1. Why? This is something you should be able to argue for the exam. Because elements of this Galois group, being automorphisms, are doubly operation preserving. So if x is a root, well, let me call it beta. If beta is a root, a 0, of f of x equals x to the fourth plus 1, so beta to the fourth plus 1 is 0. And by the way, this would mean, with this example, beta is either omega cubed, omega to the fifth, or omega to the seventh, but I'm pretending I didn't think about that here. So beta to the fourth plus 1 is 0. Now apply phi to both sides of that equation. That implies phi of beta to the fourth plus 1 equals phi of 0. But wait a minute. Homomorphisms map the identity element to the identity element. Identity under addition. Here it's a group under addition. Isomorphisms also map 1 to itself. General homomorphisms don't necessarily do that. Because it could be trivial homomorphism for one thing that sends everything to 0, but isomorphisms will send 1 to 1 as well. But anyway, by the fact that phi is operation preserving, that means you can write this as phi of beta to the fourth plus phi of 1. And yes, phi of 1 is 1 because phi is an isomorphism. But phi of beta to the fourth, by the fact that phi is operation preserving under multiplication, is the same as phi of beta quantity to the fourth. And that does it. Phi of beta satisfies the same equation that beta does. It is still a 0 of f of x equals x to the fourth plus 1. So any element of the Galois group is going to permute the roots of the given polynomial. In fact, it'll permute roots of any polynomial as long as they're in the given field that you're talking about. There's nothing special about the f of x equals x to the fourth plus 1 here. So as long as beta is a 0 of that in whatever given field extension you're talking about, it doesn't matter what f of x is. Beta or phi is still going to permute the roots. Or we are interested in these particular roots in this particular polynomial. But will any permutation work? I mean, there are 4 roots. 1, 2, 3, 4 of them. Again, these black dots. Omega, omega cubed, omega to the 5th, and omega to the 7th. Those are 4 objects. The set of all permutations of those 4 objects is S4, which has got 24 elements. So does that mean the Galois group has 24 elements? No. It's a group of permutations that in this case would be a subgroup of S4, but it doesn't necessarily equal S4. In the quintic example we talked about briefly at the end of class on Wednesday, it did equal S5 in that example, but usually it's just a subgroup. Very well may not equal a whole group. And in fact, it is very limited. We're going to see that there are going to be 4 elements in this Galois group. How else can you figure them out? Well, you can. One thing that helps you see that you've got to limit yourself is that any automorphism of this field extension is going to be completely determined by what happens, what it maps omega to. Phrase it this way. Moreover, any element phi in the Galois group is completely determined by its value on omega. Fixed as rationals, and also with those other roots, you can use the fact that it's operation preserving to figure out how it maps those other roots. Omega cubed, omega to the 5th, and omega to the 7th. We are talking about non-identity elements here. Let's say, suppose alpha maps omega to omega cubed, for example. In other words, i.e. alpha of omega is omega cubed. So alpha is going to be a particular automorphism that I'm thinking about that does this. What will it map those other roots to? What will it map omega cubed to? By the fact that it's operation preserving, it's going to map it to alpha of omega quantity cubed, which is omega cubed quantity cubed, omega to the 9th. But hey, that's the same as omega, right? Omega generates a cyclic subgroup of order 8 under multiplication of the group of non-zero elements of C, or the group of non-zero elements of Q of omega. What's it going to do to the other ones? What's it going to map omega to the 5th to? It's going to map it to omega, or it's going to map it to alpha of omega to the 5th, which is omega cubed to the 5th, omega to the 15th. That's going to be the same as omega to the 7th. It is permuting the roots here. This one's going to map to omega to the 21st. That's going to be the same as omega to the 5th. Mod 8. I'm modding the power by 8. You might also wonder what it maps I to. You know, what's omega of or alpha of I? Well, I is omega squared. So it's going to map I to omega cubed quantity squared, which is omega to the 6th, which, look at the diagram, is negative I. It maps I to negative I. You might also wonder what it's going to map square root of 2 times I to. Said that was in this field extension, right? it's omega plus omega cubed. Let's use that fact. Well, let's do it two ways. Let's first think of it as omega plus omega cubed. But I could also think of the fact that this is operation preserving under multiplication right away and write it this way. I'm going to get the answer two ways. We better get the same thing. Square root of 2I does equal omega plus omega cubed. The fact that alpha is operation preserving allows me to write this as alpha of omega plus alpha of omega quantity cubed. Alpha of omega is omega cubed. We get that. But that's the same as omega cubed plus omega. It's the same as square root of 2I. It's going to fix square root of 2I, evidently. But then I get the same thing here. Or did I make a mistake? Uh-oh. Seems like we're getting negative square root of 2I. Or did I make a mistake somewhere? Oh, I was so excited about showing you that it's the same thing either way. Omega plus omega cubed is square root of 2I. That's right, isn't it? Yeah. And then, oh, I know the problem. What am I thinking? This is wrong. It doesn't map square root of 2 to square root of 2. It maps it to negative square root of 2. I haven't proved that. Let me verify that alpha of square root of 2 is square root of 2. For some reason, I was thinking square root of 2 is rational. No. Square root of 2 is omega plus omega to the 7th. It's going to give us omega cubed plus omega cubed to the 7th, which is omega cubed plus omega to the 5th. Yep. Which is, it turns out, negative square root of 2. You can check. Adding those two complex numbers is going to bring you over here. All right. That's what alpha does. What about another element? Call it beta. Say beta of omega is omega to the 5th. To pick something else, to pick another root. Then I could figure out beta of omega cubed, beta of omega to the 5th, beta of omega to the 7th. I could also figure out beta of I, beta of square root of 2, beta of square root of 2I. I could do all those things. Let's just keep it to this. By the fact that it's operation preserving, this is going to give that, because it's going to be beta of omega quantity cubed, omega to the 5th quantity cubed, which is omega to the 15th. Mod by 8, this is omega to the 7th. It's group theory, right? Thinking about group theory. Forgetting about fields for the moment. We're going to get omega to the 5th to the 5th, omega to the 25th, mod by 8, we're going to get omega. This is going to give omega to the 5th to the 7th, omega to the 35th, mod by 8, you get omega cubed. How about a mapping that sends omega to omega to the 7th? Is it a new mapping? It would be a new mapping. Can I combine alpha and beta to get a mapping that maps omega to the 7th? What if I compose alpha and beta? See, beta of omega is omega to the 5th, so this is alpha of omega to the 5th. Alpha is operation preserving and maps omega to the 5th to omega to the 7th. Yeah, alpha composed beta does map omega to the 7th. So these are the only possibilities, because again, any automorphism has to permute these roots. And once you know the value of the automorphism omega, the rest is determined. Okay, so it's a group of order 4. Its elements, so the answer to the first question is that it's a group of order 4. And you could represent its elements as epsilon, alpha, beta, and alpha composed beta. Here's where I'm going to do like the book does, and skip the checking that it's that these things are truly operation preserving, doubly so. It was the one in the last lecture I showed you. I used Mathematica for it. I could do something similar here, and in fact, this is a completion problem from chapter 32 that I'm doing here. And in the answer key, I do use Mathematica to check that one of them is doubly out. Actually, just operation preserving and multiplication is all I check.
How do you know that there's not more than 4? Because you just pick like.
Right. Yeah, I did say that. The reason there's not more than 4 is because of 2 facts. Any automorphism here has to permute these 4 roots.
Okay.
So omega has to get mapped to one of those other 3 things or itself. And what else did I say? And once you know the value of the mapping on omega, the value on the other roots is determined. So you don't have any more freedom to make other choices for the values of, I can't just say if alpha maps omega to omega cubed, I can't just say, well, let's make alpha map omega cubed to omega to the 5th. No, it's got to map to omega. So I'm restricted to what happens. Okay, that's a good question. I was going to say one more thing. I'm forgetting what it was. So this is a group of order 4. What is it isomorphic to? There's 2 possibilities, right? Groups of order 4. What are the 2 possible isomorphism classes?
Z4, Z2, Z2.
Yep, Z4, cyclic, or the external direct product of Z2 with itself. All these non-identity elements, alpha, beta, and alpha composed beta, they have order 2, because if you compose them with themselves, you're going to get back to the identity. Alpha just really swaps omega and omega cubed, and swaps omega to the 7th and omega to the 5th. Beta swaps omega cubed and omega to the 5th, and omega to the 7th. And alpha beta swaps, well, I guess that's what alpha beta does. It's like complex conjugation. Beta swaps omega and omega to the 5th, and then omega cubed and omega to the 7th. This is a cube here, by the way. Oh, one other thing I wanted to mention is that technically to show their operation preserving, it would be good to think about the vector space description of the extension field. That's the one other thing I wanted to mention. Q of omega, since omega is a root of x to the 4th plus 1, and x to the 4th plus 1 is irreducible over q, it's not irreducible over r. I actually talked about that 5 lectures ago or something, maybe longer, 7 or 8. but it is irreducible over Q. So the degree of the extension is going to be 4. And as a vector space over Q, you can write the elements like this. And you don't have to go to any higher powers of omega there. So to truly verify that it's doubly operation preserving, you want to use that representation. And by the way, you can replace the omega squared with I if you like. Okay, so that's something you should know too. That's the vector space representation of elements as linear combinations of the basis elements. The basis elements would be 1 omega, omega squared, and omega cubed. It's a degree 4 extension. The dimension is 4. Anyway, this does turn out to be isomorphic to the external direct product of Z2 with itself. All the non-identity elements have order 2. And then, what's the lattice diagram look like, and what do the fixed fields look like? We'll quickly do that. Although, I guess for the fixed fields, we really do need the more general formula. I'm not going to have time to find the fixed fields. But the Galois group, if you think of it in terms of isomorphism classes, well, okay, let's not do that actually. The subgroup lattice, if I think of the elements like this, is going to look like this. And the subfield lattice is going to look similar, but in a sense turned upside down, though it will look the same. The indices of these things is all 2's. And the overall index of the identity, the trivial subgroup in here is 4, 2 times 2. I'll let you look up let me just say what the answer is without explaining. Here's what the lattice of subfields looks like. And this is by no means obvious. You really do need the formula for these things in terms of the vector space representation to help you figure this out. Here's what it is. It's actually this. And you'll see this in the book's problem statement. They tell you what the fixed fields are. Verifying that these are fixed fields of these different subgroups is a little bit tricky. And is not something I think you would expect beforehand. So you really do need to think about the formulas for the functions in terms of the vector space representation to help you figure that out. All right, very briefly, I do have the slide still about a quintic not being solvable by radicals. I wanted to show you what would happen if you try to apply solve in Mathematica to a third degree and a fourth degree equation. It will give you answers, but they're nasty. It won't do it for a quintic, though, in general, because Galois proved that for a quintic, it's not solvable by radicals. This could be a project for Foundations of Math, if you're interested, is to develop this theory, again, for your Foundations of Math paper to ultimately help you prove that. That would be a good goal if this is a subject that interests you. And by the way, I did find another reference that I actually bought on just a whole book on Galois theory by Ian Stewart. That's pretty good, if this is something that interests you. Real quickly, what are some advanced topics that are often covered in grad school in abstract algebra and related topics? I'm not going to go into much detail. I'm going to spend about hopefully just 3 minutes or so on this, 4 minutes. First of all, there's real abstract stuff that I kind of hinted at. There's category theory. Category theory, well, category theory, pure logic, and set theory, those are about the most abstract topics that you could possibly imagine. Okay? And you may like abstraction, you may hate it, I don't know, but that's something that typically comes up in a graduate school class. It's the abstract nonsense stuff, the diagram chasing, the commutative diagrams. It's actually, when you get into it, when you start to get it, it's kind of fun in a way. you just kind of scratch your head and you wonder what it's for. What's the purpose of this? That's kind of the heart. Okay? But it does have a purpose. Okay? Abstraction is good to a degree. It can unify different things. That's one benefit of abstraction. It can help you see key reasons for why things are true. That's another benefit of abstraction. Make your logic and thinking absolutely clear. That kind of thing. A related topic is called homological algebra. That's where you're applying category theory more to algebra, essentially. And other kinds of algebraic structures, like things called modules, tensor products. Oh, this is a great name. Functors. Functor. That's not a typo. Functor. What's a functor? Kind of sounds like it's a function, and it is, actually. Functors are special kinds of functions. Isn't that great? Functor. I love that word. It's got applications to topology as well, and the main subject where you apply this stuff to topology is called algebraic topology. By the way, these are all links to Wikipedia here too. There's something called commutative algebra, which is essentially taking what we've done with ring theory and continuing for many, many years, and discovering lots of new things related to rings, applying them to geometry, algebraic geometry, number theory. That's called algebraic number theory. And that stuff is all related to Fermat's last theorem, actually. Elliptic curves and modular forms, which also come up in complex analysis, which is the foundation of proving Fermat's last theorem. By the proof of something called the Taniyama-Shimura conjecture, which is also called the modularity theorem. That's Andrew Wiles who proved that. And he's the subject of that video that I said was so great. It's in our library as a VHS. We got to get an electronic copy of it. DVD or just some link somewhere. It's a great video, though. Gotta watch it. Got nothing else to do someday in the summer, come into Bethel's library and check it out and watch it in one of their VCR rooms. Yeah, they do still have some VCRs in a few rooms. There's advanced linear algebra. More stuff with matrices and vectors. There's something called Jordan canonical form, which was another thing that always gave me trouble on the written prelims, besides the field theory. Applications to something called topological vector spaces and functional analysis, which combines, functional analysis combines algebra, topology, and analysis all in one. It's pretty wild. And there's a mix of algebra topology and differential topology. Don't say lie. Lie groups, okay? Lie groups is a big area of application. Essentially, you're combining those subjects. You're studying group structure on smooth curves and surfaces in some way that's hard to imagine sometimes. And there's applications to physics like quantum mechanics, including something in group theory called group representation. So if you're thinking about grad school, and in particular in math, but maybe even in physics, you would see some of these topics in the future. And I think a lot of it's pretty interesting. I also feel a lot of it's pretty hard, but do your best. You can get it. And even if you're not thinking about grad school, I would hope you would be interested in at least watching the video about Andrew Wiles, if nothing else. Okay. So, all right. Review for the final exam. 20 minutes. So essentially, what I've got in this slide is a rehashing of what I sent you over email last time, but I'll give you some more verbal detail about things. First of all, definitions. The definitions that are on the test are from the recent stuff. And by the way, this is a closed book, closed notes test. I gotta think about it. There's a place or two where you gotta do some modular arithmetic, and depending on how difficult it seems when I try it myself, I might let you use your calculator. So be prepared to see a message from me about whether you can use your calculator or not, but otherwise, closed book, closed notes. Because there are some definitions and factual information to try to recall, and that is actually a pretty big part of the exam, is definitions and factual information to recall. So I'm having you do this to try to really help these things to stick in your brain, because I think it is worth knowing. Even if you don't need it in the future, I think it is worth trying to remember things that you've learned, if nothing else, just for your own personal worship of God, that you can be more appreciative, perhaps, at some point in the future of some things that you learned in the past. And if you're going to be a teacher, a lot of stuff is actually pretty good to know. Stuff about reducing polynomials. Even if you don't bring in the theory about it, deciding whether polynomials is irreducible, like with Eisenstein or something like that, could be something you could bring into a high school classroom. And you could do some modular arithmetic too, perhaps, and stuff like that. You could bring it into the classroom. Vectors and vector spaces, perhaps, at least ones you can visualize, you could bring in. So definitions, as far as theorem statements go, I'm not going to have any problem that says state this theorem. But you should be able to identify, based on knowledge of theorems, whether things are true or false. Whether for a certain thing that you figured out, or a certain question you've answered, what theorem it was that allowed you to answer that. Theorems with names in particular, like, well, going back earlier, would be like Lagrange's theorem, would be one big thing. More recent would be, for example, the Fundamental Theorem of Field Theory, also called Kroneker's theorem. You should know those name theorems in such a way that you could make those identifications. But you won't have to actually state theorems. Yeah, there are a bunch of true-false questions in it. Most of them are the same as or modifications of true-false questions from the first 3 exams. Now, I'm not taking all the old questions and putting them all on this test. I'm taking a sampling of how many true-false questions are there. I don't remember exactly. I'm going to guess maybe 10, 11, or 12 true-false. So maybe about 3 or 4 from the first exam, 3 or 4 from the second, 3 from the third, something like that, and 3 or 4 new ones. Something in that ballpark. Okay. Maybe it's even a little bit more. Maybe it's 14 or something. I don't remember. I'm just guessing there. They could be the same as old true-false questions, or they could be slightly modified. And those modifications may or may not change their truth value. The modification might change a true to a false or a false to true, but it might not. It might just be a slightly different way of saying something. For example, a contrapositive. Right? If this statement, if P then Q, is true, then it's contrapositive. If not P, or not Q, excuse me, not Q, then not P is also true. And also, if this one's false, this one's also false. They are equivalent. Their truth value is the same no matter what. They're either both true or both false. That could be an example of how I could modify something that doesn't change the answer. Yeah, some of them, maybe 3 or 4, something like that, are from the newer chapters. Vector spaces, field extensions. This was the real long, I think, extra difficult chapter. 21 was the algebraic and finite extensions. 22 was the finite fields. And 32 was the Galois. Various problems, a common type that we've done a lot with groups, counting elements of various orders in both the cyclic groups Zn, or the U groups, Un, which we now know is also the same as U of Z and as a ring, the group of units in the ring Zn. leave it the same. And then external direct products of these things. Where in the external direct product, to figure out the orders, you've got to think about the least common multiple condition. There are those problems we had about figuring out numbers of elements of various orders in the symmetric groups, Sn. See, I think of these as probably the most important kinds of things that we did in group theory as far as gaining understanding computationally speaking. Right? We do lots of computations related to those things, and it helps you understand the groups, and so that's the purpose. This says LCM condition here, by the way. Condition. Right? The order of A, comma B, comma C, say, is the LCM, least common multiple, of the individual orders of these individual elements from the factors in the external direct product. Isomorphism classes of finite abelian groups, and whether two groups are isomorphic or not. So there's factual information there. For example, maybe I give you two U groups, and the problem would be to decide if they're isomorphic or not. Hopefully the n is not too big. Though theoretically, so you can either think about the elements and their orders when you're comparing U groups, or you could think about those facts from chapter 8. So these are ones you should memorize for the test again. I'm talking about pages 160 and 161, and also those ones at the bottom of page 161, which are not labeled as a theorem, but are facts that I think are worth knowing. About the U groups, what are they isomorphic to? For that kind of problem, you could do it either way. Probably if you got these memorized, that's the quicker one. But if you don't have them memorized, then you can also think about orders of elements. And if you've got different numbers of elements of order 4, for example, then they can't be isomorphic groups. But that could take more time. So it would be more efficient to have those facts memorized. 160 and 161. Beyond definitions with regard to the field theory stuff and Galois groups, there are, so far, what I'm telling you, there's 3 computationally oriented / factually oriented questions that add up to a large number of points because one of the problems has a lot of parts. It's got 8 parts to it. Those 8 parts, most of them are fairly short, like worth 2 points per part or so. Is this ideal maximal or not? Is this factoring a field or not? Is this polynomial irreducible or not? Maybe you have to do a little bit of work for that one. Apply a test, like a degree 2 or 3 test, for example. This does include also using either long division or synthetic division with modular arithmetic to help you on one of the problems. Those are what I think of as being the most fun parts of field theory. Personally. Those kinds of calculations. And, you know, if you found a root beta, you got a polynomial f of x, say in z3x, that's maybe a cubic and it doesn't have a root in z3, doesn't have a 0. But it's going to have a 0 in some field extension by what theorem? Got a name? 2 names, in fact. I mentioned it 5 minutes ago. Fundamental Theorem of Field Theory. Field theory, not Galois theory, actually. Field theory. Kroneker's theorem, chapter 20. Some extension field where it does have a 0, but maybe even all the zeros are in that extension field. You can adjoin one of the zeros and perhaps, that doesn't mean just adding one element though, even here. Adjoin one of the elements and perhaps that adds all the zeros. Adjoin one of the zeros. I guess I usually call it beta. These are some of the completion problems too, right? You should practice those. How do you find the other zeros? If beta is a root, that means x minus beta is a factor of the polynomial. Or x plus something, I guess if it's in Z3, that would be the same as x plus 2 beta. If you do long division, you want to divide by one of those two things. If you do synthetic division, you want to put the beta over there. Put the root itself to make sure that the multiplying and adding is what you do with synthetic division. And how many elements would be in this field? Well, if this were a degree 3 polynomial, say, and it was irreducible over Z3, that would mean a basis for this field extension over F would be 1 beta and beta squared. It would be a 3-dimensional vector space, degree 3 extension. And you think about representing elements as linear combinations of those where the coefficients are from Z3, you'd have 3 to the third, you'd have 27 elements. Yikes, that would be a lot of elements to use. I probably would not give you a degree 3 irreducible, because there'd be too many elements to check, and if it was degree 3, when you divide by this, you'd get a quadratic, and then you'd have to just guess the other ones, that would be too much work. So probably, if it was a degree 3, I'd make it over Z2. And so you'd have 2 to the third, 8 elements to check total, although you can already rule out 0 and 1. And otherwise, if it was degree 2, then I guess I could do Z3, and then you'd have 9 elements overall, 3 squared. If this was degree 2. Can I clarify anything? Does any questions pop into your head about that? And yes, I am deciding now I'm going to put 2 short proofs probably. Couple short proofs. What I'm thinking of is maybe something where you need Lagrange's theorem. Or maybe the subgroup test, the normal subgroup test, or the ideal test. Or maybe something related to homomorphisms and isomorphisms. That's what I'm leaning toward. Short proofs, where you use one of those things, and probably 2 of them. Yesterday I was saying maybe I wouldn't put them on, but maybe I will. I decided that I probably should. This is a proof-oriented class, so I probably should have at least 2 proofs at the time. What do you think? Got questions? So it's Tuesday at 8 o'clock, is that right? So Monday I will be around. Want to ask me questions on Monday? Today is kind of tough. I suppose if you can stop by quickly, you can answer something quick. I am going to be gone some this afternoon, besides teaching at 2:50. But definitely Monday I'll be here all day. And ask questions anytime. Feel free to just stop by anytime on Monday. Between 8 and 4, say. thanks for being in the class. I know it was a lot of work and tough ideas, but I hope it was rewarding, or at least feels rewarding after it's done to some degree. I wish you all well, those who are graduating, which maybe it's a couple of you. Wish you well here in the future, Godspeed, and also to those who are continuing next year. Thanks.